let's talk announcements, I guess. So we have an exam on Friday, we have an assignment due on Wednesday. We have our course project due fairly soon-ish on the last day of class. So that's sneaking up on us. I would highly recommend getting started on that sooner rather than later. Come to me with questions, I would be happy to help. Questions before we dive into new content? I think I was a bit behind getting my lectures up. I came in a little bit early this morning to make sure that they were up. So they're up now in case you wanted to look back over anything. Let's see. So we were in the process of transitioning between talking about languages in general at the recursive and recursively enumerable level, and then talking about grammars and how things change if we completely unrestrict our grammars, which meant that we were going to change and now allow any number of terminals or non-terminals on the left-hand side of a production. We did say that there has to be at least one terminal or non-terminal on the left-hand side, and we can't have lambda on the left-hand side of a production. But other than that, we, with an unrestricted grammar, have complete and total freedom for our grammars. We asked about the power of them, and this is where we ended last time. We said that it is more powerful than a context-free grammar, more powerful than a recursive language, and it was exactly the same power as a recursively enumerable language. So that meant that there was an equivalence between this concept of can we accept but fail to reject versus accept or reject in a finite amount of time. So it is very possible to create an unrestricted grammar where if the answer is yes, then we can accept in a finite amount of time. If the answer is no, we may spin forever. We may never terminate the grammar, and it would be a legal unrestricted grammar. So we would be unable to say no, which is intriguing. So what would that look like? We're going to start with the start non-terminal, as always. So we need to have a start non-terminal. We have to start an unrestricted grammar with a start non-terminal. Has to happen. But then we're going to find all strings that can be derived from that start state within one step. That requires an entire parse through the grammar to figure out where can we go from here with one step. We do know that all grammars have a finite number of productions. So this list of everything that can be derived in one step will be finite. As we finish that, we're going to loop back around and find all strings that can be derived from the start state within two steps. We'll just continue this as far as we can, as many possible number of steps as we can. This process will be infinite. So we will continue to be generating new strings that are in this language. And this is, again, what allows it to be infinite. But the process itself is not going to terminate, continuing to produce new strings in the language. But you give me a finite length string, and I will tell you how long it would take you, or I could tell you how long it would take for this process to produce that string. So it's the same reasoning that we've been using throughout a lot of the past few courses, where we know this generates the entire language over an infinite amount of time, because you cannot provide a counterexample of a string in the language that this process does not generate. That said, we could get stuck if we had a query string that said, is this string in the language? We could get stuck trying to answer that question. So we can map this onto a Turing machine. We could make a Turing machine that does this. However, the converse is not as easy to show. You remember the concept of a converse from discrete? Did we go over that in our discrete courses that we took?
Sounds familiar.
Anyone remember? So we have an if A then B or A implies B statement. The converse is just B implies A. Remember, the inverse is not A implies not B, the converse is B implies A, and the contrapositive is not B implies not A. So the converse of this says, given a Turing machine, derive an unrestricted grammar that accepts the same language. This is a very long proof that I don't want to get into. It is possible to do, but we don't want to go through that process in the scope of an undergraduate class. I think just the knowledge in general of what an unrestricted grammar is, what the power of an unrestricted grammar is. So we know that we can have Turing machines for recursively enumerable languages, for enumerating those languages. We just can't assume that that Turing machine is ever going to halt. There's one more class of grammar we're going to go over, which is context sensitive. So we'll see that, actually, we probably won't see in this class, but there are a number of classes of grammars that have power in between context-free grammars and unrestricted grammars. This is an open problem in computer science, finding more of these language classes that have some kind of meaning to us. But one of them that's worth at least introducing the idea of is a context-sensitive grammar. Most of the classes that you can find turned out not to be particularly interesting to us. They don't solve any problem that we care about. So we can define this language class and say, hey, it's more powerful than this and less powerful than this. And the question that someone might ask is, okay, well, what can we solve with it or what can we do with it? And the answer is we don't know yet. There's nothing useful that that class of grammar can do. However, context-sensitive grammar is one of those exceptions. So context-sensitive grammars produce the same class of languages as linear bounded automata. What were those? What was a linear bounded automata from a couple class periods ago? Someone refresh me. Right there in the name, linear bounded.
This goes by one each time, or a certain amount.
We put the input on the tape and then we said, we can't use more space than the input allows for. So there's a beginning point and an end point, and we could have an arbitrary number of tapes as long as it's a finite number. We can't say we have infinite tapes, but we could say we have 78 tapes. But each of those tapes would be bounded to just the space of the input. So context-sensitive grammars map directly to the power of a linear bounded automata. So what would we imagine the rules of such a grammar were to be if we had to place restrictions on a grammar? Is there any intuition about what would map to the logic of, all right, we have this input, we can't take more space than that input, or at least some constant factor times that space? I'll even give a hint. So it's very similar to an unrestricted grammar, but we're going to place an existing restriction on an unrestricted grammar. So we can have any number of terminals or non-terminals, assuming it's one or more, on both the left and right hand side of any production. But what? Any ideas on that? Okay, I don't think people will have this intuition. Just curious. So the answer ends up being that the number of terminals and non-terminals on the left-hand side of the production has to be less than or equal to the number of terminals and non-terminals on the right-hand side. So we're going from fewer terminals and non-terminals to more terminals and non-terminals. Why does that turn out to be interesting? Why does that work? Well, it tells us that the length of all of the strings are only going to increase. When we go through and say, what are all the strings that we can derive in 2 steps or 3 steps? The strings that we can derive in 3 steps are guaranteed to be longer than the strings we can derive in 2 steps. The strings we can derive in 4 steps are longer than the strings we can derive in 3 steps. We know that each non-terminal maps to at least 1 terminal. And it turns out that we can rewrite these grammars into some kind of form. We talked about things like Chomsky normal form for context-free languages and Greibach normal form for context-free languages. There is a normal form for context-sensitive grammars that look something like this. So we end up with some non-terminal A that becomes a V. The form A to V occurs when A appears within the context of X comes first and Y comes after, which is why we call it context sensitive. So all of our rules now help to tell us when can we make this associated rule. Because of the left-hand side and the right-hand side, we can now grab at this context. This what comes before and what comes after this rule of some non-terminal to terminal. How are we doing with that? Any questions? Take a look at an example. It is important to note, we can't generate the empty string with a context-sensitive grammar. So our example is going to be to show that the language A to the N, B to the N, C to the N, such that N is greater than or equal to 1 is context sensitive. It is one thing to note that this is a fairly simple language to define, but oftentimes these languages have very complicated context sensitive grammars. I'm not going to have you derive this because I don't know if we would get there. But here is an example of a context sensitive grammar for A to the N, B to the N, C to the N. Take a look at this for a minute or two and see if you can answer the question, why does this represent the language A to the N, B to the N, C to the N? Where is the context? What might help is to draw this out with an example string. So see if you can apply the rules of this grammar to produce AAA, BBB, CCC. So start with the start non-terminal and see if you can apply some successive rules to generate that string. And I think that might help you to see why this grammar works. We have to start here, right? There's no way that we can possibly start here, because that terminates it immediately to produce just ABC. So we have to start with a capital ABC. What subset of rules could we apply from here? Only this rule? What's really funny about this is it literally is a rule that flips the place. This is allowed in context-sensitive languages. It says, if you see this, replace it with this. So let's go ahead and do that. This says that we can move this terminal B before this non-terminal A. So we'll produce A, B, capital AC. What's the next rule that we can apply? Are there any, do we have any choices here?
No, have to say.
We have to use the AC rule. So we're going to replace the entirety of AC with this. So this AC, we have the AB, we're replacing the AB. Sorry, replacing the AC that comes at the end here with capital B, lowercase b, CC. We have a choice of rule to apply here. We have to apply this rule. So this is going to reposition this capital B to be after the B's. So at this point, we're still missing an A, but we have two B's and two C's. Okay. Onwards, we will replace and flip this. So we have now A, B, B, capital B, C, C. What do we apply next?
You all the way back to before the first.
Yeah, so here we did this flip where we did that to there. And I did this wrong, didn't I? I wrote this completely wrong. We had this. Yeah, the B is supposed to come first. So this flips this here, not there. Yeah. See, now we can apply the AB rule to make this. We don't quite want to be done yet. If we did this, we would end up with AABBCC, right? We'd be replacing one of the lowercase a's with two lowercase a's. We'd be adding a total of one of them to this, which would get us that AABBCC. So now we can do the replacement of the AB at the front with a capital A that replaces this A capital B, and we have B, B, C, C. So you see, we could have terminated it to produce the A, B, B, C, C. But now we have this A that we can further expand. It comes right before a B, so we can swap it. So we now have A, B, capital A, B, C, C. We'll apply that exact same rule again to move the A to the end of the B's, which is what we wanted to do in the first place. A, B, B, capital A, C, C. And now we have that capital A, C. So we can make an extra C and an extra B. This is the rule that makes an extra C and an extra B. This is the rule that makes an extra A. So we'll take that AC. And A, B, B. This AC gets replaced with capital B, B, C, C. And then after that, we had one more C. Now we have 3 B's, 3 C's, and 2 A's. So we can start to move this B back toward the front, just like we did before. So we will flip it backwards twice. We have A, B, capital B, 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 C, C, C. And one more, A, capital B, 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 C, C, C. And now we can take this AB and turn this into the AA that ends it. Now we're going to select this production instead of that production because we are done. So we had an A, and we're going to replace that AB with AA. And then just copy the rest of the string. B, 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 C, C, C. Done. Having gone through that work, do we see why this works? If you just look at it without trying to draw out an example for yourself, it looks kind of confusing. But now we see that this A's purpose is to move to the end of the B's, produce B's and C's. Be replaced with a capital B, move that back to the B's to make A's. So we go to the end of the B's, make some B's and C's, come back to the beginning of the B's, make some A's. And you just do that over and over and over again. And that every time you do that once, you're adding an A, B, and C to the overall string. That's not a procedure that might be readily apparent the first time that you think about how do we do A to the N, B to the N, C to the N. But after you see it, it's kind of an, oh, well, that kind of makes sense. We just need to move here, do something, move here, do something, move here, do something, move here, do something. But grammarizing that, I'm inventing words here as I go, is an interesting idea. Questions on how that works, why that works? Let's get you to code this up. Yeah. Luckily, when we talk about theoretical computer science, we're not overly concerned with complexity. It's a matter of, is it possible to do it, yes or no? Because we're mostly looking out into the future. When we have arbitrarily complex machines, we will start to be able to do problems of larger and larger size and worse complexities. So it's just a matter of, is this eventually possible? Should we be looking ahead and seeing what we can do if we can unlock additional computational power? Granted, it still scales very poorly. But yes, that's not an ideal complexity. If you wanted to figure out what that complexity was, how would you do it?
Dependent on the number of like letters that you have in your alphabet, right?
Sure, assuming it was just A to the N, B to the N, C to the N. We would look at how many productions does it take to represent a string ABC. How many productions would it take to represent AABBCC? How many productions would it take to represent AAABBBCCC? We'd be able to come up with some kind of table of the size of the string, the number of productions it takes for that, and we can come up with an expression that maps that out. We can figure out the order of that expression. Is it polynomial? If it is polynomial, is it quadratic? Is it tertiary? Is it quartic, quintic? Terms for the third to the fourth to the fifth, or is it exponential? We could fit regression models to any of those and figure out which one it is. So here's the example. And of course, I flipped that. So we can show all context-sensitive languages are also recursive. So it's not just recursively enumerable. Now we have something that shows that context-sensitive languages are recursive. However, there are some recursive languages that are not possible to represent in context-sensitive grammars. So we can find at least one recursive language not context-sensitive. This shows that the linear bounded automata is less powerful than a simple Turing machine. Remember that when we talked about that, I said that there's a proof for how linear bounded automata is less powerful than a simple Turing machine, and this is one of the ways of working it out. The last thing that I want to introduce in this slide deck is the concept of the Chomsky hierarchy. Noam Chomsky was very interested in this and ended up coming up with this image, which is a very interesting way of showing the hierarchy of language classes that we have studied so far. Do we know what all of these stand for? Let's take a guess. What's this stand for? Regular. So this is all the regular languages. What is this?
Context free.
Yes, so that is context free. What is DCF? Deterministic context free, yes. So we talked about how there was a difference between the non-deterministic context-free languages and the deterministic context-free languages. So here's the deterministic context-free languages, here's the context-free languages. So these are all subsets of the next layer out. It looks like an onion. So I think of the Chomsky hierarchy, it's just this really cool theoretical onion. CS, what does that stand for? Besides computer science?
Context sensitive.
Context sensitive, we just talked about it, yes. And then recursive. So this is the recursive languages. And then the last outermost class we talked about so far. Recursively enumerable, regular expressions mapped to regular languages. So this is recursively enumerable. So we have now regular, deterministic, context-free, context-sensitive, recursive, and recursively enumerable as the language classes that we have studied and are able to map to each other. There's one last image of those who don't directly map to each other. So we can show from this that all regular languages are context-sensitive. We can show all deterministic context-free languages are recursively enumerable. Any smaller section we can show is a part of any larger section here. The last one is how we talk about linear languages. We talked about linear languages, linear grammars. So regular is inside of here, but there are some deterministic context-free languages that are linear. There are some linear that are deterministic context-free and some that are not. So there's some distinction there, but the overlap is all regular. If something is linear and deterministic context free, then if it's regular, then it's both of those. But there are some that are linear and context free, deterministically context free, that are outside of regular. And that's all within context free. So all of these subsets are context free. So this is the two-part Chomsky hierarchy. We have the onion and we have whatever we want to call this. I'll leave that up for debate. Someone come up with the coolest name for it, and I'll go with it. And I'll give you credit every time I teach this class in the future, come up with something that's really a fun way to describe this. A weird eyeball. Excellent. Mutant's eyeball, we will go with that. Questions on the Chomsky hierarchy? We're going to dive into one of my favorite topics, since we've already been doing it, but we're going to talk about it in more detail now and a bit more focused. So what are the actual limits of algorithmic computation? What can we write a program for? What can't we write a program for? And how do we show this? How historically have we been able to show that we can't compute something or that we can compute something? So we've discussed what Turing machines are capable of, but we need to talk about what Turing machines are not capable of. What do we think? Guesses about what a Turing machine can't do? We made Turing machines that could enumerate recursive languages. We made Turing machines that were capable of enumerating recursively enumerable languages. I've dropped hints to this. I've probably even spoiled a couple of aspects of it. Something that can't be computed at all. What was an example of something that can't be computed? Yeah, like enumerating all of the real numbers. We found that the rational numbers were possible because that was recursively enumerable. But the real numbers were not. And we have a hint here in our chat, the halting problem. And we will be getting to that here momentarily. But yes, we'll be talking about something like, could you, in general, write a write a program that took as input another program, and then as output spit out, yes, this program enters an infinite loop, or no, this program does not enter an infinite loop. Basically, does it terminate or does it not terminate? This has to be a general case program. So you have to be able to take in any program. You can make it a single language if you want. Could you write a Java program that took an input a Java program and ask the question, is this input Java program going to terminate? How would you do that? Before we try to answer that question, let's talk about two very important terms, computability and decidability. So we'll first define computable as we could construct a Turing machine that would give us some output for all of its input in its domain. So it computes the value of some function for all arguments in its domain. If it can do this, then that function is computable. we will define something that is not computable or uncomputable if no such Turing machine exists. So could we make a Turing machine for that? That is the point of computable. Decidable, on the other hand, is rather than computing the output of a function, now we just need a binary yes or no. So the problem is now a yes/no problem. If the Turing machine can answer yes or no, then that problem is decidable. If it cannot, then it is not decidable. What makes this really interesting is we can keep the problem constant and change the domain, and that can change the answer to these questions. So the domain must be clear and able to decide if it's computable or not. But of course, problems can be decidable on some domain, but not on some other domain, which is very interesting. So we're going to dive right into the halting problem, because this is a classic computer science problem, a classic computer science proof. It is the foundation of decidability proofs, because decidability proofs are a huge part of theoretical computer science. Is this problem decidable? The answer is unknown until either we can show an algorithm that makes it decidable, or if we can't come up with such an algorithm, can we do something that compares this to a problem that we know to be undecidable? So the halting problem is exactly as I just described. We're going to write a program to determine if an input program is going to halt or not. When we phrase this in terms of Turing machines, we end up with, we have a Turing machine that is going to take as input another Turing machine and an input to that Turing machine. When we apply that input to that Turing machine, will it halt or not halt? So as I mentioned, we need a single Turing machine program to do this for an arbitrary input Turing machine and input string. I've already spoiled, I think, that this is not possible. Why? Does anyone have any intuition about why this could not be done? And maybe you could write a program to represent a subset of this. Look for a while true statement or a while one statement, but that's only a subset of all possible infinite loops. Could you write a general case? Are we getting closer to the termination condition on each pass, yes or no? You could be getting closer to the termination condition, but then eventually you could be getting farther away from it. But there's another loop you could write that would not be getting closer, but not in a way that you could necessarily prove that it wouldn't terminate after some amount of time. You couldn't write a general case program to analyze the syntax. So we would have to proceed by trying to execute the program. And this becomes recursively enumerable. If it halts, we will see it halt. If it doesn't halt, we will just know that it hasn't halted yet. So that is my intuition behind this process. The process doesn't go from that route, but I think that that will help you to understand maybe a bit of why this isn't quite possible to do. We'd have to simulate the program, and if the program terminates, great, but if it doesn't, we don't know if it's going to terminate after a long period of time or not. So we're going to talk about this proof by contradiction. I'm not going to have you do this proof by contradiction. I only want you to understand it. And we probably won't have time to go into a ton of detail on it. We'll finish this off tomorrow. But we're going to start by assuming that a Turing machine exists. We're gonna call it H. So a proof by contradiction says that we're going to assume that it is possible. If it is possible, then that Turing machine exists. So H for the halting problem is going to be the Turing machine that can determine whether an input Turing machine string pair will terminate or not. So H is going to end in some final state Q sub Y, saying yes, if it accepts W, if M accepts W, and some final state Q sub N if M does not accept W. So that is the states of that. So we have this Turing machine, it's looking at M on W, starting at Q0, and it's either going to end in Q sub Y or Q sub N. Both of them are accepting states. Both of them will cause this machine to halt, to say yes, infinite loop, or no, not infinite loop. Terminates, doesn't terminate. Questions so far? So this is just the proof by contradiction. We're going to make a small change to this Turing machine H, and the result is going to be called H sub loop. If we reach Q sub Y, rather than halt, saying yes, this program halts, we are instead going to enter an infinite loop of our own design. A while true loop doesn't matter. So now it looks like this. So instead of Q sub Y being an accepting state, we are going to immediately enter an infinite loop. So now this H sub loop can only tell us, no, this program does not enter an infinite loop. Sorry, no, it doesn't accept it, which could enter an infinite loop. So small change, but an interesting one. Does this make sense? Questions so far? So remember that we enter Q sub Y if M accepts W. We know that this can be done. And it's answering no that is the challenging part. If it doesn't accept, that means that it could have entered an infinite loop. So we're going to construct a third Turing machine that we're going to call H sub proof. I've changed the names of these from the textbook to hopefully make them a little bit clearer. So if you read these in textbooks, they're not usually called something with these subscripts, but I found these subscripts to be helpful in understanding this process. So we have now three Turing machines, H that solves the halting problem. We have H sub loop that is going to enter an infinite loop if the answer is yes. And now we're going to construct H sub proof that's going to utilize these other machines that we have constructed. So this machine, H sub proof, takes what we're going to call M, that is the binary encoding of the input of the Turing machine to H. We're going to feed in the machine that solves the halting problem. After this, it's going to behave exactly like H sub loop. So it's taking it as its input, it's copying it, it ends in its initial state rather than halting. So the entire purpose of H sub proof is to copy the binary of H onto the tape, ending in its own initial state. After it does this, now we have H sub loop. So we're going to now see if, given some W, this halting problem is going to halt or not. So we encode this Turing machine in binary as a string, and we're going to call this W sub proof. So we're going to feed it itself, which is a really strange thing to think of. We're going to feed the halting problem, the program that is the halting problem. Assuming we have this solution, we're going to encode that solution and we're going to use that as the string. Does the machine that accepts the halting problem does that work on a program that is the halting problem? So making the substitution of M for H subproof, giving it as its input W subproof, we see the following. H subproof halts on W subproof if and only if H subproof does not halt on W subproof. That is the conclusion that we are able to draw. And H subproof does not halt on W subproof if and only if H subproof halts on W subproof. Both of these are contradictions. And both of them cannot be true. Neither of them can be true. So because in no domain do we have a solution to this, we end up concluding that no such machine can exist. Now, what I really want to show you is a clip that does a little bit better job of showing this visually. But unfortunately, we have 1 minute of class left, or 2 minutes of class left, and it's not quite enough time to start this. So we're going to start next class by showing you this, because I think that that helps make it very clear what this is actually doing. But I can take the last minute of class to answer any questions that you have about this idea before you see it visually. Does anyone have any confusions that I can address for the moment?
What is the main benefit of entering that infinite loop in the H loop?
Yeah, so H loop going into this loop is basically saying we can construct a Turing machine that says, if I can determine that your program terminates, rather than say, yes, your program terminates, I'm logically going to now just enter an infinite loop such that I will never be able to say, yes, your program terminates. And that becomes the contradiction. I can construct such a machine such that if I feed my machine my own code that does that, we produce the contradiction. So yeah, this infinite loop is mainly just to say, if the program terminates, rather than say, yes, it terminates, I'm just going to go into an infinite loop. This becomes the counterexample, basically, the proof by contradiction. It says, if such a program existed, if we could construct such a program that would read another program and answer whether it terminated, then we would need to be able to do that for this problem. We would need to be able to determine, yes, this program terminates, or no, it doesn't. But we create the exact case where if we would say yes, then the answer is no. And if we would say no, then the answer is yes. David, I'll answer your question as soon as I stop recording here. I do see it. So we will pick this back up tomorrow. Assignment, exam, and project, the 3 things you need to be thinking about. I will have office hours starting now. If you have questions about the homework or the project or the exam, we will have a review period on Thursday for the exam on Friday. All right, I will see you for that.